So it's my great pleasure to be introducing today's speaker, Guy Blelloch. So Guy is a professor of computer science at Carnegie Mellon University. His research is at the intersection of algorithms, computer architecture, and programming languages. So he's one of the leading figures in parallel algorithms research, and he has won numerous awards for his work, including a recent SPA Parallel Computing Award, and also the IEEE Charles Babbage Award. So his research has helped define how we think about parallel programming and has directly influenced many widely used parallel programming languages and also libraries. So beyond his technical contributions, Guy is also an excellent mentor. So Guy was actually my PhD advisor back at CMU, and I don't think I could have picked a better advisor. So Guy has trained many students who have gone on to be professors at top schools such as MIT, CMU, Cornell, and also recently UBC. So I would say Guy has a lot of research superpowers. So one I want to is the ability to find simple and efficient solutions for very complex problems. So another fun fact is also like the other is he helps us. And so today, I will be speaking about the current state of parallel algorithms as well as future directions in this area. So please join me in welcoming Guy Blelloch.
Thank you, Hal. I'm glad to be here. Yeah, so I'm going to be talking about parallel algorithms, a field I've been working on. It was my PhD thesis. I won't even mention how long ago, except I was there at the same time as Jim Little at MIT. So why do we care about parallel algorithms? Well, you've probably heard about NVIDIA so nowadays you can't buy a computing device that's doesn't have multiple cores on it, right? So NVIDIA latest devices have 26,000 cores on them. The AMD processors, single chips, have 192 cores, which is actually 384 threads since they're hyper-threaded. Laptops come with up to 24 cores. And my watch only has 4 cores, but apparently if I had a Samsung, I would have 5 cores on my watch. So the point is that machines have multiple cores. I mean, not all of these cores are made equal. The NVIDIA ones are not as powerful as the AMD ones. They're little cores, but the point is they all need a lot of parallelism, right? And so all machines today are parallel. Okay, but the state of the world nowadays, if you hear people talk about algorithms, the term algorithms, they nearly always mean sequential algorithms. Why don't, if all machines nowadays are parallel, why don't they mean parallel? And, there's some evidence of they meaning sequential algorithms. If I go to Wikipedia and I type in algorithms and go to the algorithms page, it defines it as a sequence of mathematically rigorous instructions. The sequence implies it's sequential, right? It's one after the other. Okay, so that's the sequential algorithms. If I go to a programming competition, ICPC, or even Meta Hacker Cup, or these other things, they tell you to program sequential algorithms. Okay, and pretty much every algorithms course at most universities are just focused on sequential algorithms, right? And I actually checked the curriculum here, and I guess it's what 221, 320, and 420. And I couldn't find any parallel algorithms, although Hal told me that once in a while they do a little bit of parallel algorithms in 221. But the point being is there's very little in parallel algorithms, and we might ask why. Well, one possibility is that they're just super complicated, right? We couldn't possibly describe them on Wikipedia. We can't possibly teach them in our courses, and they'd be too complicated to do in a programming contest, right? Another possibility is they don't work very well. We better stick with sequential algorithms. Maybe we can run different algorithms on different cores, right? Another possibility is okay, maybe we can hack something so it works. We all know that NVIDIA sell a lot of chips. They just had their announcement, I guess, Wednesday night, saying that they've now selling 20% more chips this year than last year. And So obviously people do write parallel algorithms, okay, but maybe there's no good theory about them, and so from a sort of, academic point of view, they're not very interesting. Another possibility is this is a social phenomenon in the sense that most people haven't learned parallel algorithms, and so therefore they don't teach them. So it's like, we don't know them, so we're not going to teach them. And in Wikipedia, the people who write those Wikipedia pages, they don't know parallel algorithms, so that when they describe, like Barufka's algorithm for min-spanning trees is a parallel algorithm, but if you go to Wikipedia, it describes it as a sequential algorithm, which I think is ridiculous. But probably whoever wrote that Wikipedia page didn't know that it was a parallel algorithm, so they thought they'd write it as a sequential algorithm. So that would be the social side. So I'm going to come back to this because, part of the goal here is to explore, which of these reasons could be true and which ones are not. In fact, I'm going to argue it's not one of the first three. It could be the fourth one, and maybe there's other reasons I don't know about. Okay, but before I do that, there's different notions of parallelism, so let me just separate them out. I'm going to be talking about parallel algorithms, and what I mean by that is an algorithm that runs on a single machine to solve a fixed problem, like to sort or to find the minimum spanning tree, okay? There's other things called concurrent algorithms. In fact, this is a topic I didn't work in very much at all until Hao and another student also from Toronto came and convinced me to work in concurrent algorithms. But it's quite different. The area there is that here you have a bunch of threads accessing a shared data structure, and the interesting questions about timings and when things arrive and whether they're linearizable. And these are different sorts of issues, okay? Because in a parallel algorithm, we have all of our data up front, all the processes are coordinating together, communicating, so we don't have to worry about these timing issues. There's also distributed algorithms, which are algorithms are running across networks and machines. In this talk, I'm really focusing on the first one, which is parallel algorithms. How do I do minimum spanning tree on a graph? How do I sort a sequence? How do I do a linear program on some, a set of linear constraints, et cetera? The other thing is my focus here is on algorithms with theoretical bounds. Okay, so I'm not talking about programming an NVIDIA chip for the latest LLM learning system. Okay, so the outline of my talk is I'm going to give a little history of parallel algorithms. Okay, I haven't actually been around since the beginning of this history. I'm not quite that old, but I've been around for more than half of it. And I'll then talk about some recent current research in parallel algorithms. And then I'll sort of come back to the original theme, which is, I'll give some examples and come back to the original theme of, why maybe we don't, think of algorithms as meaning parallel algorithms. Okay, so let's start with the history. Okay. By the way, if you have some, quick questions, feel free to ask them during the talk. So the history goes back until the 1960s. Okay, I actually claim that in reality it goes back until much older than that. I mentioned Barufka's algorithm for min-spanning trees. It was designed in 1926, and it was a parallel algorithm. So in some sense, it goes back to 1926. But actual, algorithms in sort of modern times go back to the 60s, and there was work on designing parallel algorithms for, specific kinds of networks, like, hypercubes and butterflies and meshes and various sorts of networks. So you could build a bunch of, processes, put them into this network, they'd communicate. And there was quite a bit of work and think problems such as sorting. There's a famous sort called batches, bitonic sort, and a lot of work on dense matrix routines. It turns out that this is, to design algorithms for these sorts of networks is very low level. It's sort of not portable and ugly. And so this kind of work actually lived through until maybe the until around 1990, and then sort of died off because of that reason. There was also a lot of, especially in the theory community, work on circuit models. Okay, here's where you model a computation as a circuit, and you want, and it was used to show lower bounds. It has some problems. In fact, let me go into a little bit more details about the circuit models. Okay, basically, a circuit, like I said, you can model a computation of the circuit, and then what we do is we care about the size of the circuit and the depth of the circuit. And so, if it's a shallow circuit, then maybe we can compute that very, efficiently in parallel. And so there was this class called NC that was defined, which basically are circuits which have polynomial size and polylogarithmic depth. And for a while, this was considered sort of the mark of a good parallel algorithm. If it was an NC, then it's a good parallel algorithm. If it's not an NC, it's not. And this was sort of the belief in the theory community during the 1970s. Okay. And many people showed that various different algorithms, sorting and merging and various graph algorithms were in NC. They also showed that, they also came up with this notion of what are called P-complete problems. So P is the same P as in P versus NP. It's algorithms run in polynomial time. And P-complete problems are really sort of the most difficult problems in P. Okay. In particular, there's this class of problems where you can basically, any one of them you can reduce to any other one. Just like NP is the class, NP hard problems are problems where you can reduce to each other. It's a similar sort of notion. And so there's this class of P problems, and it was, it's still conjectured. In fact, one of the biggest open problems in parallel computing nowadays is to distinguish whether NC is equal to P. It's probably as difficult a problem as whether P is NP. Okay. And so, the people identified some P-complete problems like max flow. And so the conjecture is max flow is not a good parallel candidate for a parallel algorithm because it's P-complete, which means we can't come up with shallow circuits to compute it, polylogarithmic depth without using some huge amount of size. Like I said, it's probably unlikely that any of these problems can be solved in polylog depth and polynomial size, because that would imply, P equals NC. Okay, so this was kind of nice work in the 1970s, but there was major flaw in the notion of NC being the marker of efficient algorithms. Okay, and it goes in both directions. It goes in the direction that there are NC algorithms which are not efficient in modern notions. And likewise, there are ones which are P-complete, which are very good parallel algorithms. So because it can't make this distinction, it's probably not a good model of parallelism. So I'll just give you two examples. One is, turns out that shortest path is trivially an NC. NC2 means actually in a polynomial log squared depth circuit. And you can do this just by repeated matrix multiplication. But then the work is very high. So the total size of that circuit becomes n cubed. And that is very impractical because you'd need some really, really large circuit. Now, you'd say it's still polynomial size, but in practice, that's, consider that you can do Dijkstra's in sort of near linear time. So it's n cubed versus, almost n. There's a huge waste of work. Okay, so it's saying that this algorithm is, a good parallel algorithm, well, when really it's not. And on the other side, there's lots of algorithms which are P-complete, which parallelize very well. They just don't parallelize down to logarithmic span. So they might parallelize down to n to the half. So they might, run with a circuit of size, n squared with depth n to the half, and that's a very parallel algorithm, right? It's got, the depth of the circuit is much less than the size. It's very parallel, but it's not in NC, and it's, in fact, it could be a P-complete problem. Okay, so, and furthermore, circuits are not a very convenient programming model. Okay, for those who work in, homographic cryptography or something, that's, you know that. Okay, so the next decade is the 80s. People started thinking more about, well, what is a good, more practical model maybe, and it came up with a PRAM. Okay, so the PRAM, I probably should have put a picture of a PRAM, but it's just P processors connected to a shared memory. Okay, so it's a very big model. They all work in lockstep. They're fully synchronous, so they can all do an add together. They can all fetch some element from that shared memory together. This became a very, it's a simple model. It became very popular in the 80s. There were hundreds of papers on the topics. There are probably years in there where the top theory conferences like Fox and Stop, probably up to a quarter of the papers were PRAM papers. So, a big chunk of the theory community was working on such parallel algorithms. And people came up with solutions to all sorts of problems. I've just listed actually a very small sample here. In fact, Jim Little and I worked on vision algorithms and some computational geometry algorithms, back in the time. Also, there were a lot of really cool ideas that came out of this work. These ideas of pointer jumping, random mate, a lot of these ideas, graph contraction, I mentioned contraction. A lot of these ideas actually later were adopted by the sequential algorithms community, but they came out of the parallel algorithms community. Euler-Tor trees, scan operation, sampling. In fact, sampling is random sampling is a great idea, example of something that came out of the parallel algorithms community and then became a very big thing in algorithms in general. So that's on the positive side. There was something on the negative side, which is this what's so-called transitive closure bottleneck, was actually identified by Dick Kopp around 1987, when we realized, look, we've got all these great parallel algorithms, but no one has come up anything for its shortest paths or some other related problems, directed reachability or strongly connected components. Okay, we could argue there's still not great algorithms for these problems, but I'll come back to these problems at the end of the talk. And as I pointed out, these are actually problems which are all in NC. Okay, but because we are focusing on work efficiency, and work efficiency means that we don't do any more work or very little more work than the sequential algorithm. So if a sequential sort is n log n, we don't want to do more than n log n total operations in the parallel algorithm. Okay, so if you think about the PRAM, you can define work as the number of processes times the number of steps, because that would be the total work, total operations done. Okay, so the goal was to make that work as close as possible to sequential. It's easy to come up with shallow circuits with shortest paths, but they do like n cubed instead of n work. And no one could come up with efficient algorithms for these algorithms that did work efficient for these problems. This was termed the transitive closure bottleneck by, like I said, by Dick Kopp. Okay, but this actually, there's a lot of these positive aspects of the PRAM, but they also had some problems. They're very overly synchronous. Real machines don't fully synchronize between the steps. They're hard to program because you have a fixed number of processes, P, and your program might vary the amount of parallelism it needs over time, and so you have to then map your jobs to the processes, which can become a real pain. It also ignores communication costs. So those are some of the issues. So around the same time, so this is again in the 1980s, there were a bunch of parallel machines work that came out. Okay, there was a company called Cray. I worked at that machine there. Can someone guess how many processes that machine had? You weren't supposed to answer. Bill and I worked on this machine, yeah. So 64K is the right number. So that's more than the number on the NVIDIA chip I showed. So it had a lot of processors. They were 1-bit processors, so they weren't very powerful. And furthermore, this machine cost $4 million at the time, which is, whatever that'd be, like $15 million today. But these machines, they are all very expensive, okay? And they also didn't work well with the PRAM algorithm, okay? And I'll get back to this in a second. So, people tried. In fact, some of the first work I did was trying to program PRAM algorithms on them, and they weren't particularly efficient doing it in the sense that they weren't sort of price competitive with, good sequential processors at the time. So then became the 90s, and partly motivated by these shortcomings of the PRAM, there was sort of this push towards, well, what's the next model? So I'd say 90s was sort of the era of let's look at maybe better models for parallel algorithms than the PRAM. And they went in two different directions. One direction was to make them more communication efficient, so to take account of communication costs. There's the sort of what's quite famous Valiant, Valiant's another Turing Award winner, BSP model, bulk synchronous processing model. okay, which is this model where you basically have bulk rounds, and then you communicate. And the point is it charges different amounts for the communication than for the computation. So you could take account of the communication cost. There was a similar model called the gap model, and there were various models for accounting for like cache locality in parallel machines. So, a variety of models that tried to take account of communication cost, partly motivated by the fact that these machines were terrible at communicating. Then there was also more on the programming side, and also not just programming, but just even describing the parallel algorithm. There were these nested parallel models, which is what I worked on. In fact, that's sort of what I started working on. This is my thesis, and continued working on it in my early years, and still work on it today. And these models, I'll show you an example in a second, but they basically just allow you to, fork jobs off, run them in parallel, then do a loop over a parallel loop, and you can nest these arbitrarily, these forks and parallel loops. And there's no notion of processor at all. You never mention processor in the code. You just say parallel for, or you say do these things together. Okay, and it was a much easier programming model. You can nest these, and I'll show you exactly. And then the question is, well, how do you account for cost? So in the PRAM, it's just simply, well, you have number of processors and you have number of time steps, right? And like I said, the work is just a product of the two. Here, you can sort of view it as a DAG, is that you off and you sort of create the DAG of computation, and the total number of operations you do is the work, and the depth of this DAG. So when you do two things in parallel and you join them back up, it's obviously the max of the depth of the two subcalls. The depth of this DAG becomes the span of the depth, and the work is the number of operations. The cool thing about this is it turns out this model is also, in addition to being a better programming model, also much better for communication than the PRAM was, because once you start like forking these jobs off, they become more and more local. So think of a divide and conquer algorithm. Eventually it'll fit within a processor, eventually it'll fit within a cache, and then it becomes much more efficient. So these algorithms were much more efficient from a communication point of view, as well as being an easier programming model. So here's actually an example of an algorithm. I literally took it directly from a paper I wrote in 1995, which is quicksort. So this is what a parallel quicksort looks like. Okay. It's just, think of the curly brackets as just saying in parallel. So it says, we pick a random pivot, and then we, in parallel, find all the elements which are less, all the elements which are equal, and all the elements greater. That means that key A is compared to every element in S in parallel. It's not done one at a time. And then in parallel, we make recursive calls on S1 and S2, and then we put the things back together again. Okay, so that's a parallel algorithm. If you wanted to code this on a PRAM, it would be hundreds of lines of code, because you'd have to like schedule it on your processors. You don't know the relative size because it's quicksort. Maybe you're unlucky with a pivot, maybe you're not. So you don't know how many processors to dedicate to one of those recursive calls and how many to the other. There's all sorts of problems you would get into if you tried putting this on a PRAM. So this nested parallel model is effectively what people still use today, at least if you're talking about shared memory parallel algorithm. You can analyze the work and the depth of this algorithm. This block diagram is sort of showing you what the so-called the DAG might look like. Is right. You have the top level quicksort that does the selection of all the elements less, equal, and greater. And it makes two parallel calls, and they make two parallel calls. And the point is, everything that's horizontal can be done in parallel, while the things which are vertical have to be done sequentially, right? And so the depth of this recursion tree is log n. And it turns out the depth of each of those blocks, because you have to do this filtering. I do have a mouse here, right? You have to do some filtering here of the elements that this takes log n depth to be able to pack these elements down. But you end up with a depth that's, certainly polylogarithmic. So this is a very efficient parallel algorithm from a theoretical point of view. You can also show it's cache efficient. Okay, I don't want to get into this, but you can extend this model to assume that you have caches with certain line sizes and cache sizes, and show that it's an efficient algorithm in this model. But I'm not going to get to that. Okay, so that's sort of, we're at sort of the middle of the 1990s, okay, and we hit the parallelism winter, okay, and basically parallel computing died for about 10 years, okay, and we can talk about the causes and the effects. Well, there are several causes. One is that those machines I showed you, a lot of the companies went out of business. The MassPower went out of business, thinking machines went out of business. The machines were too expensive. They were hard to program efficiently, okay? I just showed you an easy way to programming it, but that was an academic work. It hadn't made its way to, practice yet. Sequential machines were improving at an incredible rate. They're improving at the clock rates of sequential. Every year and a half, they doubled the clock rate of these sequential machines. When I started working, they were running at 1 megahertz, right? Now they, by 2005, they're running at 2 gigahertz. So.
I kind of looked at the difference between parallel and concurrent, because that decade is also an amazingly flourishing decade for the design of multi-core machines for commercial workloads.
For this decade here?
Yeah, that decade is depending on when we get the sun machines for.
Yeah, so those are still pretty damn expensive machines, right? Those are like 500,000.
Parallel.
No, that was still parallel. I'm going to get back to multi-core, yeah, in a second. Other things that, but I say one of the big causes was the .com. So some of you don't remember, but I'm very aware of the .com because at the beginning of my career, .com hit around 1992 or 93. I was a young tenured professor at the time, and all of a sudden, all anyone talked about was like the internet, and I wasn't doing the internet. And so I was wondering, am I going to be able to get tenure without doing the internet? And I feel for people today who are not working on AI, because they probably feel just like I did at the time. I think it was very similar. So the effect of this was that there were very few theory papers, and there are actually quite few, there were some systems papers, but not a whole lot. And furthermore, no one was trained in parallel algorithms. And this will come back to the societal effect of why we don't think of parallel algorithms. Someone mentioned algorithms, because there was this whole 10 to 15 years when none of us students, even our PhD students, learned anything about parallel algorithms, because they were learning about .com instead, right? Just like nowadays, you might be learning about AI instead, right? So that lasted in 2005. There was something special that happened in 2005. I don't know exactly the reason, and it probably wouldn't happen exactly 1 year. But all of a sudden, all the manufacturers of these machines who were doubling their clock rate every year and a half stopped. Okay, there's just hit some technological limit that in 2005, all of a sudden, machines at the time were running at between 2 and 3 gigahertz. How fast do they run now? Between 2 and 3 gigahertz. Okay, they have not improved since 2005 in 20 years. Okay, up until 2005, they were doubling every year and a half. Okay, so this was, a major hit, because now it says we can't improve the sequential speed. So instead, we have to do parallelism. And indeed, Intel delivered their first consumer-grade processor, basically cheap processor with 2 cores in 2005. And they also gave a roadmap that said they'd get up to hundreds of cores by 2020. Okay, they didn't quite meet that, but they're up to hundreds of cores now. So maybe they're 5 years late. Okay, but they had a pretty accurate roadmap of where they were going to get to. Okay, so all the improvements since 2005. And this, by the way, they're still doubling the number of cores every year and a half, and that's still true. Okay, we keep seeing the number of cores increasing. Like the 192 core AMD, a year and a half ago, the biggest one was 96 cores. Okay, so with that, now people argue that that's also going to run out at some point, but for now, we're doubling the cores. So as an effect, there was, in the systems community, there was a sudden excitement, and most papers and system conferences started to focus on parallel computing. The theory community was a little delayed, and I think there's a couple reasons for that. One is probably the theory community was not impressed by having 2 or 4 or 8 cores, right? When you talk about asymptotics, that's clearly a constant, and who cares about constants, right? And the other feeling was, this fool me once, a lot of people had worked in PRAM algorithms, and I think a lot of them felt that their work went wasted because there was sudden winter, and all their papers that they'd written in the 1980s hadn't been cited in 10 years, right? Because no one was writing follow-up papers. And so they felt, oh no, why would I ever work in parallel algorithms if, my work goes unnoticed, right? So I think there was a bit of this. I don't know how much of each, or maybe there were some other reasons, but it was slower to take up. So I claim until 2015, it was still the case that there were very few papers in theory conferences on parallel algorithms, okay? On the other hand, there's been a significantly uptick since around 2015, and I don't think there was any special event around 2015 other than it was just a slow, and it was also not exactly 2015, it was, over some years around there, increase in interest. And there are lots of different things that started picking up. I was going to just spend some time at this talk, which is also coming into what are the sort of the cool new ideas in parallel algorithms. So I'm going to talk about some of these. So I'm going to talk about 1, 2, and 3 and some of the new ideas, which is basically analyzing dependencies in sequential algorithms, batch dynamic algorithms, and we get back to this transitive closure bottleneck. If you remember, this is this problem where we couldn't come up with efficient algorithms for things like reachability and shortest paths. There was also been quite a bit of work on, other models. The MPC model is a variant of the BSP model I mentioned before, which there's been quite a lot of work on. So there's probably been, dozens of papers in theory conferences on this topic, and some other models as well. I'm not going to go into these. Instead, I'm going to focus on 1, 2, and 3 and some new, some of these, new topics in parallel algorithms. So let me stop here. Is there any questions about? Okay. So, at this point, by the way, 2015, we were probably at the point where multi-cores had on the order of a single chip had on the order of 16 cores, and you could easily get, 4-chip systems or even 8-chip systems. So you could easily get 64 cores. And they're typically hyper-threaded, so that means 128 threads. So maybe part of the pickup on interest was, yes, 128 is a constant, but it's starting to look like more than a constant. Okay, so what I wanted to do is, this is actually the only technical part I'm going to go through in the talk. I thought I'd give you one cool idea in algorithms. So this is, like I mentioned, this analyze dependencies in sequential algorithms. There's this, people noticed, or, I worked on this and other people worked on this, that certain sequential algorithms have dependencies on them. In other words, they're not trivially parallel at all, but if you carefully analyze them, you can actually show that the dependence depth is shallow, in the sense that if I ran things as soon as everything I depended on was ready, I could then get this to run in, logarithmic depth instead of linear depth, for example. So this example here is what's called Knuth's shuffle, is one of the oldest algorithms, around within Knuth's original book. And it was how to generate a random permutation on an array. And it's a very simple algorithm. Is you basically start at the end of the array, you pick a random number between 0 and I, which is the current iteration number, so your position, and you swap with it. So basically means you start at the end and you swap with someone before you, or at you or before you, and then you go to the next one. And if you think about it, this will generate a random permutation, because every time I swap someone to the end that's a random element from the people before you, right? So this will generate a random permutation. And it's a very simple algorithm. And at the time, there had been PRAM algorithms for random permutations, but they were very complicated algorithms compared to this. There were 100 lines of code instead of 4 lines of code, right? So, so we were looking at this and we're saying, well, maybe this algorithm really is parallel. Okay, so let's look at this algorithm. So let me just go through an example. So in this algorithm, the I here is my position, and let's say that that's the actual, value I'm storing there. And the h of I is the random number I pick, right? So the first one, it picks the index 1, so it means I'm going to swap the first element, index 1, remember the 0 index, with the last element. So the b and the h are going to flip, so we flip that, right? And then the next step says I'm going to switch with 3, because at position 6 we see h of I is 3, so we swap those, right? And that's how the algorithm goes. So if you think about this, it's kind of could be extremely sequential because there's a lot of dependencies. Like if I swap, let's say I pick, those are the HIs that I happen to pick. If I say 7 swap with 6, then I'll swap with the two of them will swap. But then I have to do that before the next swap, because I'm now going to swap the 6 with the with a 5, and then I'm going to swap the 5 with a 4, and then the 4 with a 3, then 3 with a 2, etc. So there's a very strong dependence chain here. In fact, the dependencies are a linear length, right? And so I end up basically having an algorithm that runs in, that it has a dependence chain of log n, so it's completely sequential. Okay. Now, of course, that's an unlucky flipping of the coin. It's very unlikely I'm going to pick 6, 5, 4, 3, 2, 1 in my random numbers, right? Well, what if I pick these numbers? That's also another possibility. In this case, it's completely parallel because everyone swaps with itself. Okay. So the dependencies, this particular algorithm, are sort of data. It depends on the random numbers that I pick. It's data, the dependencies, it's a redundant terminology, is data dependent. So the question is, well, I'm really picking random numbers. I'm not picking 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5, 6, 7, or whatever the two choices are. I'm picking, something that looks more like this, right? Some set of random numbers. Okay. And then I can ask, well, what are the dependencies like in here? Well, if I swap 7 with position 1, okay, and if you look at here, there's 3 1s in my array. I'm later going to swap 4 with position 1. So if you think about it, is 7 is going to end up at this position, this 1, right? Because it's going to swap down to 1, and then it's going to swap up to here. So that's a dependence. And then later there's this other one, and that's going to have another dependence. Okay. So it turns out that the dependence chain here, if you think about it, looks like that. So those things have to happen sequentially. You have to first swap 7 and 1, and then 4 and 1, and then 2 and 1. In order to make this correct, I have to do it in that order. I can't do them in parallel. Okay. And there's some other dependencies I'm not showing here for lack of time. But then you say, well, assuming these are random numbers, well, what is the expected number? What's the expected depth of dependencies in this graph? Okay. And it turns out, if you make random choices, that you can show this has log n expected dependence depth. Okay. And furthermore, it turns out that you can detect these dependencies very easily by just looking at indices, and you basically compete. So, for example, if I go back here, say, how would I detect is if they all wrote, it assumes that you can do a write with min. If they all wrote their index to position I, you would then detect that, 7 was the first one that had to happen. So if you were the maximum to write there, then you're the one that can happen. Otherwise, you have to wait. So you could actually easily build a parallel algorithm based on this dependence depth. And so that was the idea. And so then you could, and it actually isn't that much code. In fact, I'll show you the code if we have time at the end, to make this work efficiently. And you can apply this not just to random permutation, but a whole bunch of different problems. Maximal independent set. So what's the sequential maximal independent set here? It's the completely trivial algorithm which says maximal independent set of a graph is we're going to find a set of vertices that are not neighbors. And then maximal independent set. So a trivial algorithm is I put the vertices in some arbitrary order. I pick the first one. I knock out all of its neighbors because they can't be if I'm in it. So I add the first one to the independent set. I knock out my neighbors because they can't be in it. and I go to the second one. If it's not knocked out, it does the same, and you leap through it. It's, again, 4 lines of code, right? It turns out this one also has shallow. If you do this in random order, it has shallow. And the maximal matching is a similar one. As you take the edges, matching is a set of edges that don't touch each other. Again, you put them in a random order and you knock them out one by one. Okay. This one also has shallow dependence depth. Okay, Knuth shuttle I mentioned, 2D linear programming, Delaunay triangulation, all of these have shallow dependence depth. So what it means is a lot of sequential algorithms are actually parallel. Okay, if you look at them a little more carefully and you analyze them. Okay, and I'll show you that actually coding this up is not. And then furthermore, the algorithms based on them are work efficient in the sense they do no more work than the sequential version. Okay, so if this is one line of work, I did quite a bit of work on this. Others did, work on it too. By the way, I apologize. I'm not giving citations because I started throwing in citations, but I would have like 10,000 citations because so many people have worked on parallel algorithms. Right? Okay, so that was one. So I said there's sort of 3 recent directions. So this is work that was done sort of starting in around 2015 and going on. It's still going on. Another sort of fun direction, this came out, the reason this was not done in the 1980s with PRAM algorithms was that at the time, dynamic algorithms were not a hot topic. So let me first define what a sequential dynamic algorithm is, which is sort of a cool area of algorithms. Is what you have is you want to maintain some property of some object, let's say a graph, like the minimum spanning tree of the graph, and then I'm adding and deleting edges to it. And then I want to update what the minimum spanning tree is, or what the clustering is, or what the, there's many different properties I could maintain. And so I want to do this efficiently. I don't want to recompute from scratch. I don't want to have to, I add add one edge, I have to redo my MST. I delete an edge, I have to redo my minimum spanning tree, et cetera. So I want to do this efficiently. And there was a lot of work in the 90s, during the parallelism winter, in fact, on work on dynamic algorithms, sequential dynamic algorithms, one update at a time. Okay. So what's people have been looking at now is what's called batch dynamic algorithms. So instead of doing one update at a time, I want to do multiple updates. Okay. And this is actually motivated by a very real problem that, if you go talk to people at Google or Facebook, they work with graphs. Okay. Because the social network is a graph, right? The friendship graph, and they do all sorts of graph analytics on it to find, like when they try to figure out, who to suggest as friend, it's some graph algorithm that's running over your graph, doing that. Or Google does its PageRank, and so PageRank is some graph algorithm on the web graph, and they have all sorts of, I actually consulted Google. They do all sorts of clustering algorithms and graphs, and in fact, there's a huge group at Google that does graph algorithms. But their graphs are dynamic. I mean, the web is obviously not static. Facebook, social network is not static. Furthermore, the number of changes, it's not one at a time. That there's a lot of changes, especially if they, batch them up. They can do it much more efficiently if they could do it in parallel. And the advantage of doing a batch is now you can do it in parallel. You're not doing it one at a time. You could do like 100 updates or 1,000 or 10,000 or, a million updates at once on a graph that's very much bigger. The graphs I'm talking about here are, 100 billion, right? The size of the social network graph is, in fact, hundreds of billions. So that's one motivation for these batch dynamic. It turns out they also can be used as substep in other parallel algorithms, and I'll give some examples of that. And there's actually a third improvement is that even when you batch a bunch of updates, you can actually make each of them faster. So you can take advantage of the fact that you're doing them together and make it so that on average, the cost is less than doing them one at a time, the total work. So anyway, there was a lot of work on this in the last, as you can see, this is still going. Many of these papers are from 2005. In fact, more than half of them are from 2005, right? So this is a hot topic at the moment. There's been batch dynamic algorithms for, various algorithms on trees, for graph connectivity, minimum spanning trees, graph matching, Cornice decomposition is a graph analysis technique that's actually used for social networks. For graph spanners, for those of you who work in the theory of parallel algorithms, you almost certainly know about graph spanners. Same with expander decompositions. These are all important subroutines in various graph algorithms. So this is a sort of a cool topic that's ongoing. It's also, I mentioned that these algorithms get used in dynamic algorithms that use as part of static algorithms. So you can actually use a dynamic algorithm to build a static algorithm. And there's been, a handful of results on this. There's minimum cut work that we had done in 2021, and then other people did work on parallel depth first search and min cost flow. In fact, this last result's a very nice result. It takes, some of you might have heard of these recent results where they've made max flow and min cost flow nearly linear time, if you're in the theory community. And this was generalized to work with parallelism, work efficiently, and it uses these dynamic algorithms, batch dynamic as substeps. Okay, the last of the sort of hot new topics in parallel algorithm I wanted to go is coming back to this transitive closure bottleneck. So if you're going to ask me what the most important result in parallel algorithms is in the last decade, I would put the first one of these, the reachability by Feynman. That's right. This is the only one I attach a name to, because I think it's that important as the most important result. Because I had mentioned that it had been, and I'll explain the results itself in a second. No one since Dick-Karp, who's a pretty smart guy, it's another Turing Award winner, came up with this notion that these problems are hard in 1988. How many years ago was that? 37 years ago. He identified these as hard problems, and no one had made any good progress on them since then. So remember, the problem is to take reachability or shortest paths and come up with an algorithm that's nearly work efficient, that does close to what Dijkstra's does. So we all know Dijkstra's algorithm, it does m log n work. So we come up with an algorithm that doesn't do much more work than m log n, okay, and get some speed up. And before this result, the first one, there were no algorithms that were known that did, by the way, O tilde, for those who are not in the theory community, can someone in the theory community tell them what O tilde means? Now, O tilde means big O, but with ignoring logarithmic factors. Okay, so that means we're hiding some logs in there. So when I say O tilde M, it means O M log to the K of M. Okay, I'm not going to tell you what that K is. It depends on the algorithm. So again, to be work efficient, Dijkstra's is m log n. So you'd like something that's O tilde of m. And nothing had been known that had depth less than n. It was like this barrier. There's no algorithms that were even sort of partly good. Until then, since Karp did it in 87 until 2018, there wasn't any result in that area. So this result by Feynman finally showed that you could get it down to like n to the 2/3. You might say that's not great, so that's the depth of the circuit, right? But it's at least progress. Okay, so now you could get circuits which are done. And then quickly people improved on it. So the following year it was improved to n to the half. And I think that's what it stands at now, but I could be, there might have been more improvements. I haven't actually followed that. And then soon after that, people started, like I said, there were a few problems in this class of, the transitive closure bottleneck. Another was shortest path. And there was first, there was just an approximate shortest path, okay, in 2020 that broke this barrier, okay. And it also had, n to the half. In fact, I think it was even less than, something like n to the half. And then it was, first an undirected graphs, then it was improved to directed graphs, and then it was improved to be exact, and then it was on one of those two is, this is all for the z greater than or equal to 0 means that these are only positive edge weights, like we have to assume in Dijkstra's algorithm, okay, shortest path. The last one actually works even for negative edge weights. Okay, and that's sort of impressive, and it follows with some recent results from sequential algorithms that also showed negative edge weights. So basically, in a few years, we've like significantly improved the state of the art on this particular problem. So at least from the point of view of theory, I should point out that this is not very practical. So this is very, very cool from a theory point of view. These algorithms are incredibly complex, and I'll have a comment on that at the end. Okay, so I just want to get back to my original question, which is, you know, parallel algorithms don't make it in the mind think of most people. Most people's mind think of an algorithm is probably what they learned in their sophomore year data structures course, right? You think of quicksort or something, and when they think of quicksort, you're probably not thinking of the parallel version of quicksort. You're probably thinking of the sequential version, right? So the question is, you know, is it time that we, you know, Wikipedia actually describe parallel algorithms? You know, should we be teaching in a class? And I should point out at CMU we do sophomore level algorithm data structure class teaches parallelism from day one. In fact, it teaches sequential algorithm as a special case of parallel algorithms. It's just parallel algorithms where the depth happens to equal the work. Okay, because once you go to the work depth model, that's true that, you know, I don't have to put a parallel 4 in there. I just write it without a parallel 4. It's exactly the same programming language. It's just the work equals the depth. Should programming competitions start using a little bit of parallelism? After all machines are parallel. You know, should there be more research? I guess that's, you know, I'm not going to force people to do research they don't want to do, but. So I just want to address this a little bit by showing that. Coming back to the questions, you know, well, maybe parallel algorithms are not efficient in practice. Well, that's, you know, not completely true. I'm sorry that this is probably too small for many of you to read, but I can tell you what the bottom line is. It's a list of 19 different graph algorithms. This was in a paper that I wrote with my prior students, Julian Sun and Lakshman Dulipala, where what we did is we coded up theoretically efficient parallel algorithms for a whole bunch of different problems. So these are algorithms where you can prove that they have a bounded work and, you know, bounded depth, and you can show the bounds. So these are all theoretically efficient algorithms. And what we showed is that you can get really fast speed up. Okay, and this is fast speed up relative to the best sequential algorithms. Okay, and so we're getting speed ups on, you know, on a machine. This machine had 72 cores. And we're getting speed ups up to, in fact, 74 in that bottom number. Can someone tell me why we could get speed ups with more than a number of cores? Why? Hyperthreading, yeah. So each of these cores has 2 threads. So there's actually 144 threads. So, yeah, so you theoretically good algorithms can also be practically fast. Okay, so it's not that there's some disjoint between the theory and the practice. So I said that was one of the possible reasons people don't do parallel algorithms. That's not it. Okay. And we've coded up, this is a list of, we have this ParlayLib is a library for programming parallel algorithms in C++. And we have dozens, I think there's 85 algorithms in there now for all sorts of standard problems. These are sorts of problems that you'd come across in your, you know, intro data structures course, or even your upper level data structures course. So in addition to the graph algorithms, there's, you know, there's Karatsuba's algorithm for matrix multiply, all sorts of edit distances, etc. And so these all, and they're all reasonably simple. Okay, so you can code them up, and I was just going to go through a few examples in a minute. But the point is, we also measured the sort of speed up on here, and on this machine, this was a 32, it's a different machine. This has 32 cores, but you can see, you know, again, it has hyperthreads, so you can get more than 32 speed up. But, you know, there's some of them, you know, there's one in there that's pretty low. I guess this is at Lasso is a machine learning algorithm. For those of you know what Lasso learning is, it's a regression algorithm. But the rest of them, you know, do quite well, right? I mean, you don't get perfect speed up, but you wouldn't expect it. So these algorithms work. So the point is, and they're all theoretically, you know, analyzed algorithms. So that's sort of like, okay, so they're efficient. So that's not a reason. And the theory matches the practice, okay, theory never perfectly matches practice. And I'll be honest here that there were, in the design of these algorithms, there was some thought to locality as well. So, but whether it's sequential or parallel, you always have to think about locality. Like the FFT, there's some, it's, carefully designed for locality. So then there's a question of, in fact, let me start with a different algorithm. Breadth first search is, well, how complicated are these algorithms? Okay, so this is breadth first search as written in that library. Okay, I'm not going to have time to go through it completely, but just think of it as an algorithm that in parallel starts at a node and then visits all of its neighbors. It's like, a shell algorithm, and then it visits those neighbors. That's all that this is doing. Okay, now the work of this is linear, so it matches the sequential work. Okay. And the depth of this algorithm is going to depend on the sort of diameter of the graph. Because the number of levels that you have to go out is going to be the diameter. So it's not going to work well on a linked list, for example, but it's going to work extremely well on a social network or a World Wide Web, because those all have very, we all know social networks, what's it, 6 degrees of freedom or whatever. So the furthest two people away from each other in this graph is, some number less than 10. So D is 10, let's say. So this works very well. And in fact, if we go back to this graph here, breadth first search is the first one, and that's basically what I'm showing. So what I'm showing is those times with a 68 speed up is effectively this algorithm. I should point out there are some optimizations in that. So maybe this only would get, half the speed of the one I mentioned. But the point is, so it's not that it's difficult. It's not that it's slow. Okay. So those aren't reasons. It's not that the theory doesn't match the practice. So we're sort of left with the social aspect, right? The social aspect being maybe people haven't learned parallel algorithms. Maybe they don't know what they look like. Maybe they don't know it's simple. Oh, by the way, this is a Knuth algorithm. Okay. There's this speculative for, which is a little bit of magic. It basically means run through these iterations, but run them in parallel. And, I don't have time to explain this completely, but it basically is a way to guarantee that things which depend on each other don't run at the same time. But this ends up with what the code looks like for this is, remember, the randomized swap algorithm I showed. This is the parallel version that makes sure that things get run in the right order. Okay. So yeah, so the claim is, I guess my selling, what I'm trying to argue here is that, maybe it's time that we spend more, actually people learn parallel algorithms. That maybe the, academic world or Wikipedia, descriptions or programming contests are a little bit behind the time. And I guess that's pretty much the end of my talk. So just want to conclude, parallel algorithms have made a lot of progress in the last 50 years. There are many simple and practical parallel algorithms today. And again, I'll put a caveat here is shortest path. Yes, I mentioned those great results, theoretical results at the end. You probably, if you looked carefully at mine, I had shortest paths in my list of things, but I said its depth was proportional to the diameter of the graph, which means I was cheating, that, it's not theoretically efficient. To make it efficient for any graph, those theoretical bounds hold, they're not practical. Okay, so that's an open problem. In fact, I think I have it listed in my list of open problems. I think that these ideas, like we teach them in our intro course, it'd be great if other people did. And I didn't talk much about locality. I mentioned it once briefly, but it turns out you can extend these models I discussed to account for, cache hierarchies and locality. There are many cool open problems, if any of you are interested in parallel algorithms. I mentioned some parallel batch dynamic algorithms. There's many open problems in batch dynamic algorithms. There's, again, coming back to this reachability, I think a big open problem, is there a simple solution to problems like shortest path and reachability, a practical solution that's also theoretically efficient? A problem that's completely open is strongly connected components. No one knows how to do that. Even among those new results I showed, strongly connected components. It's actually one of the original problems that was listed as having the transitive closure bottleneck. The other problems in that class have been solved. This one's open. Then there's this very big question whether P equals NC. It's probably as hard as answering that whether P equals NP. So if you take this one on, you know, you're taking a risk. And the other thing is, you know, I talked about parallel algorithms, but I think a lot of the cool interaction is like mixing parallel algorithms like with concurrent algorithms. The focus in concurrent algorithms hasn't been on runtimes, it's been on correctness, just proving that these algorithms run linearizable. In other words, they look like this, they run in some consistent order in a composable way. And there's little work on time bounds, and the work there is on time bounds is pretty poor, okay? So it'd be really cool to come up with concurrent algorithms which have nice theoretical time bounds, and there's not much work on that. And that's all I have, and so that's my view on parallel algorithms. Yeah. Any questions? Yeah, in the back. Okay.
One style of parallelism that is popular,
I did. It's called the MPC model, right? That's the new name for MapReduce, right? But yeah. So the MPC model, yeah. So it's some new models, right? So the MPC stands for massively parallel computing, and the model is you have a bunch of processes. You assume the computation on the process themselves is completely free, and you just count the number of rounds. But the limitation is each processor only has sort of n to the you know, epsilon memory or something like that, or n to the 1 minus epsilon memory. And yes, there's been a lot of work on that, and I don't have time to talk about everything. Plus, I should say I'm a little biased towards my own work, and yeah.
Wonderful. I think I had a question or a comment, right? So most algorithms courses, even when dealing with sequential algorithms, don't have students implement anything. They typically analyze this. And I think the challenge then is how do you appreciate parallelism when you've not even implemented a sequential version of a fairly complex algorithm, right? Where you see what the speed up looks like. So a typical algorithms class is analysis and zero implementation. Which I think is part of the challenge. And then you have to say, what am I going to test it on? Do I have a standard platform? So I think that. Well,
yeah, I'm not suggesting that an algorithms course has to do programming. I'm saying that the algorithms course, when they analyze quicksort, they should say, this is a parallel algorithm. They shouldn't say it's a sequential algorithm. They should say, look, we can compare the key to all the all the elements to the key at once. We can do the two calls in parallel. And if we do that, we can calculate. The work is actually the same as the analysis and sequential algorithm. So there's no extra work in that. And the depth is just the depth of the tree. So you just analyze it in work in depth, and you don't have to do any programming. So it's just a question. When you tell the students to analyze time in the sequential model, they're just taking your word that that's a good model, right? They don't have any proof that's a good model, right? They're taking your word. So if you tell them that the work in depth is a good model, they're just going to take your word and they're going to analyze it in that. And so that's what I'm kind of suggesting.
Other thing that you can talk about, but in that sort of winter of 1990, at quantum computing sort of molecular dynamics, but in which sort of manifestation, so there was implementation.
Yeah.
That and sort of wondering where you saw that as beginning.
Yeah, I guess that's why I put this comment at the very bottom of this slide. Because that really did not have work on theoretical bounds, most of it. Now, there's a caveat that some of the work, especially like Jim Demmel at Berkeley, did have theoretical bounds, but only for a very narrow class of like matrix operations, which were, important for some of these scientific computing. Yeah. I mean, at the time I was working I have several supercomputing papers, so in fact, that's sort of where I went during the winter to hibernate.
Yeah, because I also, using it, this map, the MapReduce model allows you to think about depth and work kind of sometimes easily, and it seems like a easy way to introduce it in an algorithm's context, maybe.
Yeah, so you could do that as well.
And
You have a question?
Well, yeah, here's one kind of tricky guy.
Oh, gotcha. Okay.
And the second one, you put up one of the open questions was P equal, whether or not P is equal to MC.
Yeah.
Now, wouldn't that be, I mean, that would strike me as being almost as surprising as proving P equals NP, because, if I can write an interpreter for sequential programming, right, that can run a polynomial time, sequential program on polynomial time, then you can parallelize my interpreter and everything becomes parallel.
Yeah. I guess what I meant by that was more likely the proof would be that they're not equal.
Okay.
So, yeah, sorry, I should have said it proved that either way. My belief is they're not equal, just like, yeah, they're as likely to be equal as P equals NP. Yeah. That's a good point. Yeah. Oh. Oh. Hi, Margot.
Incorporate memory hierarchy model, fabulous. And so my question is on those great speedups that you showed us, how big was the data, and in particular, at what level of the cache hierarchy did it fit in memory?
The data was the biggest graph that's out there, that's publicly available, the 200 billion edges. I think it actually listed it, but this is the, oh, we didn't mention. Yeah, so this, sorry, I should have put that in. This graph is the, I forget what it's called. It's, yeah, it was the biggest graph that's available, 200 billion edges. Yeah. Yeah, even main memory, you need a big memory machine, yeah. Yeah, so this is a big graph. Okay, any other questions? There was one. Yeah. Mm-hmm. Yeah, so the question was like in the work of Jim Demel, a lot of it's on communication avoiding algorithms. So I mentioned some of those models, like the BSP is also a communication avoiding model, right? That it charges more for the communication than not for the communication. But you're right, a lot of that work was for distributed machines using like MPI type algorithms instead of shared memory. And a lot of the work I'm talking about is for shared memory machines. That's correct, yeah. So my personal view is that if you can fit it in the memory of a single machine, you're very much better off doing it on a single machine than a distributed machine, okay? And furthermore, the very biggest publicly available graph that we're able to get now today fits on a single machine. So everything you can do with that, you should be doing on a single machine. A, because it's easier to program, and B, it's much more efficient. Now, that being said, I consulted Google, and they have non-publicly available graphs that don't fit on a single machine, that order of magnitude bigger than what I just mentioned. And so in that case, I guess you have to go to a distributed. Furthermore, if you're doing some very large simulation, it's possible, like supercomputing simulation, it's also probably not going to fit on a single machine. So it's not that this will work for everything. Yeah.
What was your experience like teaching parallel algorithms along with sequential algorithms to undergrad, at the undergrad level?
Our students, so we teach these to first semester sophomore year. This is our Intro to Data Structures and Algorithms course. They have no difficulty understanding the parallel part. Okay, they have the same difficulties. When I used to teach just a sequential course, the same course when it was just sequential, it was, they have difficulty solving recurrences. They have just difficulty with general problem solving, but the parallelism doesn't really add much challenge to it. And you know, you can come interview students if you want to double check on that. Okay, so that means I get.